Hello, and thank you for clicking on the video PowerPoints for Chapter 8 in your Modern Welding textbook, Gas Metal and Flux Core Arc Welding. This chapter is a lot of information. We're not going to go over every slide in this chapter in this video. A lot of it is going to be the hands-on techniques that we're going to use in the shop. So I'm going to save a lot of those PowerPoints and that information on those PowerPoints for when we're actually in the booth and we're doing our welding. I did post on D2L the full list, 74 PowerPoint slides that are in the chapter. So if you do want to go over, after you've done reading, if you want to go back over and look at the PowerPoints for the chapter, you're more than welcome to under the content chapter 7 or chapter 8 on D2L. Because there's a lot of information, let's jump right into it. Chapter 8, Gas Metal and Flux Core Arc Welding. Our learning objectives: contrast MIG metal transfer methods, considering arc characteristics, welding characteristics, and out-of-position welds. Select the proper arc welding machine, wire feeder, shielding gas, flow rate, contact tip, nozzle size, and welding wire type to produce an acceptable weld. Identify the different shielding gases used for MIG and explain how they affect the shape and penetration of the completed welds. Properly assemble and adjust all the equipment required to produce an acceptable weld using MIG and flux processes. Make acceptable welds on all types of joints in all positions using MIG. Again, those are some of the slides that I'm not going to go over in this video, but we will go over obviously in the shop. Make acceptable welds on all types of joints in flat and horizontal positions using flux. Identify potential safety hazards associated with MIG and flux products. All right, MIG and flux. Gas metal arc welding processes use a solid welding wire that is fed into the pool or puddle. Flux is similar to MIG, but uses a welding wire with the flux inside the wire. Flux has the advantages of both MIG and stick. Just like stick, it has a slag on the outside protecting the weld, and just like MIG, it uses the same exact setup as a MIG setup. Flux can be done with or without shielding gas. We talked about that last chapter. You can have flux single shield or self shield or inner shield, and then the flux that we'll be using is the dual shield. So you'll have the flux inside the core wire, and then you'll have the shielding gas as your second shield for your weld. Welding principles: MIG is nearly always performed with direct current electrode positive. That would be your gun is hooked up to your positive in your power supply, and your ground is hooked up to your negative on your power supply. A variable wave form is possible with an inverter power supply. There are very thin glass-like islands over the weld bead after MIG welding. That is from the silicone in the deoxifiers, the denitrifiers of the welding wire itself. It's not slag, but it will be like a flaky type glass, what they are calling glass-like islands. You can just brush it off with your wire brush or a wire wheel. A slag covering, though, is present in flux, just like you would have when you're stick welding, which you'll have to clean off every time because we don't want slag inclusion on our next weld. Welding principles: gas metal arc welding. If we take a look at the figure, we see the wire coming down through our contact tip. It's also known as our electrode. Our gas nozzle is surrounding our contact tip. We have our shielding gas coming out around our wire. For the flux core, very similar setup, exact same setup, except for the electrode or the wire. The metal is on the outside of the wire. On the inside, it's filled with flux. Metal transfer: molten filler metal is transferred from the electrode to the weld pool by different methods. The 4 methods: short circuit transfer, globular transfer, spray transfer, and pulse spray transfer. For short circuit, that'll be MIG. Globular transfer you can also run in MIG, but you can only run in the flat and horizontal position. Spray transfer is what we're going to use for flux core dual shield, and the pulse spray transfer will be for MIG pulse. Short circuit MIG, short circuit gas metal arc welding, is used with relatively low welding currents Short circuit transfer is particularly useful on thin metal sections and to fill large gaps. The combined effect of surface tension and the pinch force separates the molten metal and the electrode. So if we look at the picture here, this is the sequence of metal transfer. The metal short circuits to the weld pool. You have your shielding gas surrounding our weld pool. Pinch force squeezes off a droplet. So that's where the wire comes out. It pinches the electricity. The arc pinches it and pulls it into our puddle. The arc reignites, and this process is done over and over again in short bursts. If you look at it like this for short circuit, when you hit that trigger, your wire starts coming out the end of your gun. When you have your workpiece grounded and you're completing that electrical circuit, the arc jumps out of your workpiece, pinches the wire on your gun, coming out of your gun, and starts to create your puddle. When you're short circuit welding, always try to remember to stay in your puddle. The initial startup to try to get your puddle started, I'd like to do little circles until I get a puddle started, because that wire comes out, it pinches, it hits again. The wire comes out, pinches, droplet, it pinches, droplet. Once you get that puddle started, it runs a little bit smoother. When you first start up, you're going to have sparks flying everywhere. You know, it's going to be carrying it on. It's kind of a pain in the butt. But if you constantly stay in your puddle, it'll run smooth. You'll start to get that sizzling sound. It almost sounds like you're frying bacon. If you get out of your puddle though, and you get on that bare base metal again, that short circuit popping, it's gonna start flying sparks everywhere, and it's gonna become a mess. So we want to stay in that puddle, make it run nice and smooth. Short circuit MIG, an ideal short circuit transfer rate and the pinch force can be obtained by properly balancing the induction and slope. Shielding gases may also have an effect on short circuit transfer. Inert gases must be used on all non-ferrous metals. Globular transfer, our second metal transfer method. Metal transfers across the arc as large irregular shaped drops. To minimize spatter when using CO2, current is increased slightly to create a buried arc. Let's look in our book. So basically the way we go from short circuit to globular is just increase our voltage and our wire feed speed to the point where we're getting more deposit at a larger rate, at a quicker rate. So we have an irregular large droplet forming, and our arc is jumping off, having our pinch force. The shielding gas envelope is protecting our weld. The droplet may short circuit when it falls, and then the droplet may fall erratically and cause spatter. So it's getting out of control. We only are able to do globular transfer in the flat and horizontal positions. If we try to do it vertically or overhead, it's just going to droop and sag on us and get kind of ugly. If you had to fill, like if you had two 1-inch pieces of steel and you were trying to do a groove weld to join both of those together, globular in a flat position, globular transfer wouldn't be a bad idea. You're going to deposit more weld. Your rate of speed is going to be quicker. So filling that joint up would actually be easier. But in most cases, in most scenarios, it's not that easy. It's usually you're welding out of position, or you don't need that much deposit to fill a joint. So globular transfer, again, it can help you at times, but in most cases, it's not really. In most cases, it's not really used. Our third metal transfer is spray transfer. Spray transfer occurs when very fine droplets of metal form at the tip of the welding wire. Spray transfer takes place only when the shielding gas contains a high percentage of argon. We're going to use this in our flux core welding. Our argon would be 75% to 25% CO2 mix. If we look at stage 1 of this, we have a larger envelope of shielding gas. The wire next down, and our arc starts to, our pinch force creates from our arc, You can tell like our arc is starting to become more similar to what you would see at a car wash with the water hose, the wand itself. Spray transfer is going to have a similar arc where it's kind of like a power washer. You know, you have that fan look to it. It's easier to work with. It's higher voltage and higher wire feed speeds. So the spray transfer, it's nice. A lot of students like flux core a lot easier than short circuit or globular because the weld itself, the bead is a lot more wet. It's easier to manipulate. It washes a lot easier. You move a little faster. It's just there's not a lot of sparks like you have at the short circuit. Like I talked about, that pounding. You know your puddle is more loose and wet than for short circuit. The welding machine current must be set above the transition current. The spray transfer method produces deep penetration. Another reason why we use it with flux core. Flux core in the industry is used on heavy equipment, heavy machinery, like you're talking in the railroad industry, you're talking the industry that I was in, at Hemp Brothers, construction, you're welding on heavy material, thick base metals, so we want that deep penetration. So here, yeah, spray transfer is best done in flat and horizontal welding position and on metal over 1/8 inch thick. Pulse spray transfer, electrical control circuits within the power source cause the current to pulse from low current level to high current level. At the high current level, spray transfer droplets leave the electrode and enter the weld pool. So even now more, instead of that constant current, constant voltage that we have with just regular spray transfer with the pulse, you're going to have peaks and valleys. So if I set my voltage at 20 volts, in its peak, it's probably going to run at 22. In its low, it's going to run at probably 18. But it's going to go up and down to kind of maintain that 18 volt setting. You still have like the spray kind of look to it. Your arc, and again, it's more fluid. Students seem to run it, even out of position a lot easier than they do flux core or the short circuit. Background current is present, and to maintain the arc, very little spatter is created. Large diameter welding wire can be used, and this transfer method is used with silicone brazed welding wire. We don't really have to worry about that. We tried that last semester. It didn't go very well. MIG and flux power sources. MIG and flux welding power sources provide a constant voltage. MIG and most flux core is done in direct current electrode positive, which would be your gun is always on your positive and your ground is your negative. Inverter power sources, smaller and lighter than traditional transformer rectifier machines, the little box welders that you're seeing more often. And they also may provide a choice between constant current and constant voltage. Two important variables used to set the welding parameters for MIG is your voltage and your wire feed speed. The wire feeder may be built into the power source or it may be external. We talked about that in the last chapter. The XMTs, the Miller XMTs, it's external for the wire feeder, and then for the Lincoln Power MIG 350s, it's internal. If we go to right now, I'm in D2L under the content and weld 120 settings. If you look in this document that I loaded to the D2L, it'll list each welder, like the Miller XMT, the wire we're using, the gas we're using, the feet per hour for our setting for pressure floor welding. And then I have the voltages, wire feed speeds, and amps used for each position. This you can reference at any time. Probably be a good idea to make a copy of it or print it out and have it for you. Keep it in your welding bag. Obviously, when you're going to get in there to the shop, there's going to be lots of students welding on the machines. So their settings and these settings might be a little off. Again, these are just parameters. We got to find out like how you weld so that we can kind of dial the machine into, like, if you like to run a little bit slower, we're going to have to, dial down the welding feet per, wire feed speed. If you like to run faster, then we'll dial it up. Just know that everything kind of runs in concert. So if we turn our voltage up, we're going to turn our wire feed speed up. And vice versa. If we turn our voltage down, we're going to turn our wire feed speed down. We don't want to kind of move them back and forth. If one goes up, the other goes up. If one goes down, the other one goes down. And like I said, this is, just the kind of the settings that I've learned over the years working in the shop. These aren't exact, but it's a good start, and then we can kind of build off of how you weld and what's best for you. Setting up the MIG and flux station, connect a separate wire feed unit if required, mount the welding wire reel onto the feed, determine what shielding gas is required, check that the regulator and gas flow meter are attached properly, check hoses and fittings for leaks, connect the welding gun, and connect the workpiece lead. Again, we're going to go over all of this in the shop, but let's see if your book has some figures or illustrations. So here's a figure in the book showing you kind of how to place the electric wire spool onto the post, and this would be an internal wire feeder in a machine. So our wire comes off our reel right here. This is our tensioner for our drive rolls. We would pop this down. This would pop up. You remember our drive rolls had those grooves on them. This one obviously feeds from the top. We won't want to put this reel in backwards and have it feed under and trying to do one of these numbers. We want to have that wire coming off so it comes right in through this electrode inlet, goes right across our drive rolls and into our liner for our welding gun. Once we have it in the inlet for the welding gun itself, we pop this back down so both drive rolls are on clamped down one another, then take our tensioner, put it back on. If you can see this picture back here, it's telling you if flux core or MIG, you want a flux core, you want to have it on a 4, MIG, you want to have it on a 5. So if I screw this down, there's the numbers on here that correspond with the process that I'm doing. That makes sure that these drive rolls have enough tension that it will pull that wire in through and out the end of the gun. Here's a look at a welding machine. We'll just kind of go over each. It's similar to what we have with our XMTs. Our XMTs are a little bit smaller with the power supplies, but the wire feed is similar. Obviously, we have our reel. Our drive rolls are internally inside our wire feeder. This is where we would hook up our gun to. This is the trigger for the gun that's going to move your drive rolls. This is actually going to have our gas hose and that hook up too for our gun. If we look at the dials on our wire feeder, the first one is our voltage adjustment. Our second one is our wire feed adjustment. With the wire feed adjustment on our millers, it's in 75, increments of 75. So if I have it on a number 2, it's actually a 150 feet per second. So wire feed speed. So you just want to make sure you want to check that. If you're on a 1, you're on 75 on our machines. If you're on 10, you're at 750. I talked about the jog switch. That way you can kind of push your wire out at a little bit at a time. You don't have to stand there and hold the trigger. And then your purge switch will actually check your gas for you. Instead of having to pull the trigger, you can use a purge switch for it. Down here, the machine itself for power and on and off switch. Here we have some of the settings in the book for the different metal transfers. It's always a good idea to look at these and kind of compare them to what you're running at. If you, like I said in the last, earlier part of the video where I have my settings on D2L, you can kind of compare them with that. If we look at the first one for short circuit carbon steel, 035 is the diameter of the wire that we're going to be using in class. They have from anywhere from 16 to 22, and the amperage range from 80 to 190. So what I like to run for our short circuit in our shop is I like to run 16 volts uphill, and I run at 150 on my amperage or wire feed speed. For flat, I run anywhere from 18 volts to 20 volts, and then I also run a little bit higher. I run 225, anywhere from 225 to 300. It's going to be different. Every machine is going to be different. When we get to, like, say, the Lincolns, the 350 power MIGs, if you want to run short circuit on those, where you put the wire in, you lift that cabinet up, there's going to be a whole graph on there similar to what you see here. It's going to have the thickness of the metal, it's going to have the voltage, the diameter, all those different factors on that graph, and you kind of got to look down and over and up, and it'll tell you a lot. And those, again, are just parameters. It's not scientific. And then if you set it up inside those parameters somehow, and you still don't like how the machine's running or the pace it's running at, that's when you got to kind of change it and dial it into the way you want it to run. You want to set the machine up the way you want it to run. You don't want to have to be bound by how the machine is set up. So that's a big thing in this course, not only just the hands-on portion of making good welds, making strong welds, but also being able to set up the machine and set up the machine how you want it to run. Another slide for setting up the power source. The power source must be adjusted based on the following criteria. Types of base metal that you're going to be welding, whether it's carbon steel, stainless steel, aluminum. The base metal thickness, how thick it is. The thicker it is, the hotter you're going to have to set the machine up. The type of diameter of the welding wire. The type of diameter of the welding wire also corresponds with your drive rolls. Remember how we talked about that? If you have 035 wire, your drive roll's got to be 035, and also your contact tip has to be 035. Transfer method to be used. Remember how we said if you're going to try globular, you're probably only going to do that in the flat position. If you're going to weld overhead, your voltage and your wire feed speed is going to have to be turned down. Type of shielding gas that's used. Remember, if you're going to do pulse, you're going to have tri-mix. If you're going to do short circuit, you're only going to have a 75-25 argon CO2 mix. Setting up the wire feeder. 2 mated gears are located in the wire drive unit. 1 gear is driven by the electric variable speed motor. A roll is attached to each gear. In a 4-roll gear feeder, 2 rolls are driven. Setting up the wire feeder. Over time, an adjustment may be needed to the wire guides. The wire can get jammed and cause a bird's nest, tangle up the wire. You don't want to do that. Obviously, you'll have to re-rig the whole entire your whole entire line, or your lead in your gun to get it to work right again. This happens to me a lot of times when I'm fishing. This is what happened to my reel. It's the same thing in welding. It's a pain in the butt. But let's take a look in your book. Here's a little better picture, more of a close-up picture of what I was talking about a few minutes ago. You can see our tensioner with our numbers on it. This picture here probably corresponds with these numbers as far as the process you go. We didn't talk about this inlet wire guide. That's usually going to correspond with your drive roll size, the grooves in your drive rolls. See, this one is 030 wire. So there are differences. The two most common, though, would be 035 and 045. But this pin here just kind of helps guide our wire through our drive rolls, and then you can see our liner sticking out. That coil right there is already our liner for inside our gun. This knob here also secures that cable. You have an adjustment. This locks these drive rolls in. To take these drive rolls or change them out, you got to spin this over so it lines up, and then you can kind of pull it out. So finally, select and install drive rolls that have the same groove diameter as the welding wire. The final adjustment is to apply the proper force from the drive rolls to the electrode. That's with that tension control. Wire feeders often include an inch switch and jog switch used to feed the wire gun and to dial in your gas. When the purge switch is pressed, the shielding gas will flow out. And it's a way that, like I said, you can kind of set up your gas. Speaking of shielding gases and gas mixtures, shielding gas cylinders can be ordered with a single shielding gas or a premixed shielding gas mixture. Gas mixtures can also be created in a gas mixer. Like I said, for flux, we'll be using the 75% argon, 25% CO2, which Airgas calls star gold. And then for the the MIG pulse, we'll be using argon, helium, and CO2 mix, which they call Stargon VS. So if we ever have to get cylinders, just make sure the difference. If you're running the pulse on the Lincoln 350 Power MIGs, there's going to be Stargon VS, and then for the short circuit and flux, you're going to be running Star Gold. Inert gases and gas mixtures. We saw this slide last chapter. Each shielding gas and mixture has a different effect on the shape of the bead and the penetration. Our mix is going to have that wide and deep penetration. The argon and helium and carbon dioxide, we're going to get penetration. We're going to get a wide bead. That's why the pulse. A lot of companies are going to pulse instead of the short circuit. Argon results in a high current density arc, deep penetration, a narrow bead, and almost no spatter. It is an inert gas most commonly used for welding non-ferrous metal, so it doesn't have iron in it. If you're just using pure argon, that's when you're welding aluminum. Helium transfers heat through the arc better than argon, is often used to weld thicker non-ferrous metals. The only difference is helium is a lot more expensive than argon, so most companies you're only going to run argon. Carbon dioxide has a high thermal conductivity, requires higher voltage than argon. It's the only reactive gas used alone as a shielding gas. But remember, carbon dioxide, bad fumes, nasty to work with, cloudy, it's tough to see your puddle. So you won't, I think very rarely will you see carbon dioxide. If you did, it would be only for using it with flux. For MIG, carbon dioxide is used only for short circuiting or globular transfer. CO2 is the most common shielding gas for flux. Argon helium produces a balance between deep penetration and stable arc. Argon carbon dioxide helps eliminate undercutting when carbon steels are welded with spray transfer. Again, that's the one we're going to use, Star Gold. Argon oxygen, added oxygen improves weld contour, makes the weld puddle more fluid, and eliminates undercut. Helium, argon, and carbon dioxide. This is our MIG pulse used when welding authentic stainless steel or short circuit transfer. You don't know why it's only here. They only have it for short circuit transfer. It's used for MIG pulse a lot. I mean, the Airgas representative said that it's like their biggest seller now because a lot of companies are running MIG pulse. Shielding gas flow rate. Enough gas must flow to create a straight laminar flow. Turbulent flow can draw in atmosphere and cause the weld to become contaminated. When too little gas flows, the weld area is not protected and the weld can become contaminated. Set the proper flow rate using your flow meter. It's better to have more flow than less. If you don't have enough, you're going to have porosity. So I would always err on the side of more than less. Like I said, on that sheet for the settings, I have a parameter in there. Maybe hit the middle, see how it runs, see what your bead looks like. If it's not, doesn't look right to you, or doesn't sound like it's running right to you, add a little more gas. Selecting gas nozzles and contact tips. The gas nozzle delivers shielding gas to the weld area in a smooth flow. Nozzles are available with different exit diameters. The contact tip makes the electrical connection between the welding gun and the electrode. We talked about that last chapter. And you're going to have to change them regularly because of that. It's through the hole, it's kind of sliding on the side. It's going to oblong that hole. Eventually, you're going to have a burn back. You're going to have to change it and replace it anyways. Contact tips have different inside diameters and lengths. Different lengths help obtain different transfer methods. Here's a picture of all different kinds of nozzles and contact tips. You have more defined ones, bigger ones, smaller ones. Selecting gas nozzles and contact tips. Resisting heating of the electrode takes place after the welding wire exits the contact tip. A long contact tip minimizes electrode extension and reduces resistance heating of the wire. We'll talk about electrode extension coming up and stick out. Contact tips wear must be changed regularly. Clean spatter out of the nozzle is needed to maintain good flow of shielding gas. I'll also have in the shop spatter gel. I recommend using it all the time to make cleaning your nozzle and your contact tip less, you'd have to do it less. It's a gel that you dip your gun in, your nozzle in, not like dunk it, but just the end of it. So any spatter that collects on your nozzle or the contact tip, you can kind of easily take off, or a lot of times it just bounces off of it. The gel kind of lubricates it to the point where it doesn't collect on there. If you have a buildup of spatter on your nozzle or inside your nozzle, it's obviously going to obstruct your gas flow, so porosity could end up happening. Also, too, if it's really globby on the end of your nozzle, that metal could stick to your workpiece while you're welding, and then obviously it's going to stop you from being able to weld any further. So we want to keep that stuff clean. Hopefully it's clean when you come into the shop, and I want it to be clean when you come out of the shop. Let me know if someone's not cleaning their nozzles, because it's not fair to spend the first 5-10 minutes of class just cleaning your nozzle and contact tips so you can weld. We want to try to keep everything looking nice and neat. It's just going to be easier on everybody, less time cleaning. It makes for good welds. You don't have to worry about porosity. So that's a big thing. Use the gel, clean the tips, make it better for everyone. Assembling the front end of a MIG unit or MIG gun. Obviously, we talked about this in the last class, but your diffuser comes it's screwed into the end of your neck of your gun. You can see the holes right here. That's going to diffuse the gas, the shielding gas for your weld. Your contact tip gets screwed into your diffuser. In some cases, for the Lincoln Power MIGs, it'll get screwed in. For the XMT, it'll just kind of sit in there. You kind of tighten it up if you have to with your welpers, and then your nozzle goes on over top. Selecting and installing a liner. A liner protects the cable from the continuous wear of the welding wire. One type of liner is a hardened steel wire wound to form a tube, and a second liner is made of Teflon used for aluminum wire. So obviously we're not going to be welding any aluminum, so we'll be using the hardened steel wire one. Just make sure, we shouldn't have to be changing liners. They should last quite a while. Just make sure when you're going into your booth and you're stretching your lead out for your gun, don't be yanking on it. If your wire gets stuck, don't be yanking on that wire that you could pull or stretch or ruin the liner. Liners should last quite a long time. We shouldn't be having to change them all the time. Selecting the correct welding wire. The welding wire must match or be compatible with the base metal that you're being welded. So carbon steel has to have a steel wire, aluminum with aluminum, stainless with stainless. Follow all specifications when selecting the proper welding wire. Once the correct welding wire is selected, it should be loaded into the wire feeder. The correct size and type drive rules must be used. If you're using 045 wire, your drive rule's got to be 045, and your contact tip's got to be 045. Preparing metal for welding. To produce quality welds, the base metal must be properly prepared. Metal surfaces are cleaned mechanically and chemically. If the metal being welded is expected to remain oxidized prior to welding, select a welding wire with more deoxidizers. Joint designs are similar to those used for stick welding. Depending on the metal size and thickness, tack weld every 3 to 4 inches. Our pieces are going to be, 7 inches if they're 3/8, and 7 inches long if they're 3/8, and if they're 1/4 inch, I think they're 6 inches. They're a little bit skinnier. 2 tacks, 1 in each end of your pieces should be sufficient. Tack welds can be feathered out, making it easier to join the weld bead with the tacks. I can show you once we get in there how to feather out a tack. It's just easier, so when you weld over top your tack, if you grind it down and feather it out, it'll look like the weld pass, the weld bead will look the same throughout the joint. If you don't, if you go over top of one of your tacks, you're going to tell. Your bead's going to have a bump in it where your tack was. So it is good to kind of clean your tacks up. Electrode extension. Electrode extension is the amount that the end of the welding wire sticks out beyond the end of the contact tip. A long extension may cause too much filler metal to be deposited, resulting in shallow penetration. In spray transfer, if the extension is too short, proper preheating of the wire does not occur. Also with that, you can kind of get worm trails or worm tracks when you're doing flux core. Once we're into the shop and you can see them, I can give you an idea what they are. So here's two figures in the book, one with a long contact tip, one with a short contact tip. Electrode extension is referring to the end of your contact tip to the end of your wire. You can see the difference in both with the different size contact tips. When I say stick out, that's what's most commonly you're going to hear out in the field or in the shop. Most people are not going to say electrode extension, they're going to say stick out, and that is referring to the distance from the end of your nozzle to the end of your wire. Most situations, you're going to want that to be about 3/8. In flux core or MIG pulse, you can run it a little bit longer. I wouldn't go any further than 3/4 of an inch with your stick out. This reason, because the further you get away with your nozzle, the more likely your shielding gas is going to go out the back door. It's not going to get to your weld, and it's going to cause porosity. Anytime you see porosity, stop what you're doing, and you know that you're getting too far away or you don't have enough gas coming out of your flow meter. Welding techniques. Most arc welding processes require the welder to control the following in order to obtain a good weld: arc length, which we just talked about, welding speed, gun angle, and gun motions. Let's take a look in your book. Here's a good chart in your book for MIG and flux electrode extensions. For MIG short circuit, 1/4 inch to 1/2 inch. Your welpers, when you cut your wire with your welpers, if you stick your nozzle right up to the end and cut, it's a 3/8 length. So it's right in between what the book says, 1/4 inch and 1/2 inch. MIG spray transfer, that would be for the pulse. Like I was saying, 3/4. The book is saying the parameter is 1/2 inch to 1 inch. The dual shield flux core, what we're going to use, so remember I said 3/4. I wouldn't go any further than 3/4, but the book says you can go up to 1.5 inches. The thing with the flux core, if you get too close, the gas is going to, it's like almost just be like being too far away. If you're too close, it's going to ricochet and the gas is going to spread. You could get some porosity. The worm trails, like I was talking about, is from your gas leaving too soon. So you want to have some distance. You want to get back. Don't get so close with your nozzle. In this figure from the book, we see direction of travel, and we're going to want to use a push angle for almost every weld we make in this course. There are some exceptions where we want to use a drag angle, maybe for MIG pulse and flux core overhead welding. For everything else, I would recommend a push travel angle or forehand welding. Just kind of a refresher, if I'm traveling in the same direction as my arc, I'm pushing. If I were to travel against my arc, I would be dragging. I would start out with push welding. Every employer that I've worked for, when it came to MIG or flux core welding, they wanted you to push. It's a lot easier to make the bead look a lot nicer. It makes a pretty weld. You can move a lot faster. You can see where you're going. And that's what I would recommend. That's what I want you guys to start out doing. Once you get more advanced throughout the course, if you want to try to start dragging, making it look nicer, you can do it. Like I said, once we get to overhead, I would recommend you dragging. But when we get in there, when we start out, we want to start with a push. When we're running a bead, we want to work to keep the edges of the bead straight and the nozzle constant distance from the base metal. I would recommend 3 points of contact. Use a forearm or a wrist or a hand, and then hold the gun along with that. We want to kind of keep steady, keep that stick out distance from our nozzle to the end of our wire consistent the whole way across. Use your table to kind of slide your hand across too. Make it easy on yourself. Don't try to make it too hard. That 3 points of contact, your feet on the ground, and then, like I said, another point, whether it's your shoulder up against the wall or something. You want to have that balance. You want to keep everything nice and consistent. Maintain a consistent travel angle. So our travel angle, like I said, we want to be pushing. Adjust travel speed to produce a bead that melts into the base metal and at the toes of the weld and has a proper width. The best advice I was ever given about welding was stay in your puddle with your arc and hold your sides. So if we start out our arc, our puddle, and we get that puddle to the width that we want, so our toes or edges of our weld at the width we want, keep that arc in our puddle and move that puddle or manipulate it however you want, but keep it that our sides are constant. You're going to have a nice straight weld, a nice flat weld, and it's going to be consistent across the entire length of the joint. So stay in your puddle, hold your sides. You're going to hear me say that ad nauseum, but I think that is the best advice to give young welders or any welders to make a nice looking bead. Running a bead, weaving creates a wider and flatter weld bead than a stringer bead. Stringer bead, there is no manipulation. You just strike the arc, you let the arc or the puddle get to its width, its whatever, say it's 1/4 inch or 3/8, and then just hold that the whole way across your joint. I like to have some manipulation, whether it's short circuit or flux core, MIG pulse, whatever. I like to do some kind of manipulation. For MIG only, because there is no flux in MIG, you can do the circles. You know, whether it's this way or that way, oval, large oval, that's fine. If you do that with flux core, it's pretty inevitable that you're going to add flux into your weld when you're circling back around, which is going to be slag inclusion, which is going to be bad for your weld. It's going to make a weaker weld. It might even have porosity coming out the top of it. So for MIG only, MIG short circuit and MIG pulse, you can do the circles. For flux, to get your bead wider, you can use either a W weave or a Z weave. This will also be what you use when you weld uphill. Again, a weave, any kind of manipulation that you do to your puddle across the weld joint. If you just keep it nice and steady, that's called a stringer bead. Any kind of manipulation, it's a weave bead. Stopping and restarting a weld bead. Do not fill the crater if you're not at the desired end of the weld. Before restarting, clean the previous weld bead. So kind of grind it down just like you do your tacks, feather it out. Position the gun and electrode wire about a 1/2 inch in front of the existing crater. Pull the trigger, move the arc back. It's almost the rear of the existing crater. This remelts the existing weld, so you kind of tied everything together and then move the arc to lead to the leading edge of the weld pool and continue. Again, that would be more for your solid wire. For flux core, I would never recommend going back and forward. Once you pull that trigger, you create your arc, create your puddle, move that puddle across the joint. Don't ever come back. Once you come back with anything that has flux in it, slag inclusion is going to be your biggest problem. You don't want to be going back and forth. It's the same way with stick welding. And I think the book tells you the same thing with stick. I'm telling you from my experience, if it has flux, don't ever go back and then forward again. With MIG and solid wire, it's different. It doesn't have that, so you can you don't have to worry about slag inclusion is the big thing. Shutting down the station, close the valve on the shielding gas cylinder, drain the shielding gas out of the system, turn off the wire feeder, turn off the welding machine, coil the cable up and hang up the gun, coil the ground and hang it up. Again, we just want to make sure that when we're coming into the shop and leaving the shop, it looks the same. We want to try to take care of all of our equipment. We don't want to have it looking sloppy and being disrespectful for the other students that have to use the equipment too. So again, we'll go over this more when we get into the shop, and I can kind of show you how to set everything up with the hands-on portion. But yeah, we just want to make sure when we leave that shop, if everything's swept up, we have our tables ground, and everything's hung up so the next student that comes in, they don't have to mess around and fix everything back up. And we're coming down the home stretch. Finally, MIG and Flux troubleshooting guide. When troubleshooting, first identify and check items that are known to cause a problem. Next, checks the equipment setup and weld technique. Finally, check more difficult items such as worn cables, grounding issues, and problems with the design of the weld. Anytime you're having issues, come get me. We'll try to figure it out. We'll try to fix it. If not, there's not everything that I can fix, so we'll just, we'll have to call somebody in to do it. Just if you don't know how to fix something or troubleshoot something, don't just kind of keep doing it, because that can make multiply the problem. So just stop, turn the machine off, come get me, and we'll try to fix it. MIG and Flux safety, wear a helmet with the approved lenses to protect the eyes and face from arc radiation. Remember, any exposed skin, be careful with that. Layers. Also start with your lenses, your shade as high as it can go, and then kind of work your way down if you're having trouble seeing. Wear PPE to protect against radiation and burns. Wear clothing with flame resistant materials. Weld in a booth with a shield, welding area, protect others. I know a lot of people like to take the drapes, wrap them up so they can walk in and out freely from their booth. Just remember, if you're going to do that, I want your back towards the entrance and exit of the booth. That way, when someone's walking by, which everybody does, they rubberneck to see what's going on in the booth. They're not getting an arc flash or a welder's flash. Just kind of have your back to the entrance. Or especially if you're coming in, if you're in one of the booths that are in an entrance or an exit to the welding shop itself, we definitely want to make sure that we're not flashing everybody going by. Do not weld in wet or damp areas. The big thing would be your gloves. Make sure your gloves, it's going to be hot in there, especially in the early fall and then in the late spring. If you start to sweat, make sure you change your gloves out. Do not touch energized parts of the welding gun with bare skin and wet gloves. Arc weld only in well-ventilated areas. Take use of our ventilation system, those fume collectors, but just don't have it too close that it's collecting your shielding gas. We want it to collect the fumes, not our shielding gas. Arc weld only or use ventilation or filtering equipment as needed. Everybody should have a mask on, so hopefully that's helping your lungs too, and not spreading the COVID-19. Take steps to avoid breathing carbon monoxide, ozone, or other harmful gases. Final slide. Do not weld on any base metal with chemicals on them. We shouldn't have to worry about that, except for cutting oil. I would grind, just clean all your material before you weld. It's going to help you out as far as the way your weld looks, how it welds. There's lots of benefits, so just get used to it. You're going to have to get used to it anyways, cleaning your material before you put a weld on. Treat all metal in the welding area as if it's hot. So once we're done at the end of the night, put hot on your pieces, put them on the big table. Don't just throw them in the cans for scrap, because people like to use that stuff for practicing before they start welding on their pieces. I would just recommend don't ever reach in those buckets or cans without gloves on. Just like it says, treat all material and the welding area as if it is hot. Use your pliers to handle a lot of material. There's a squinching bucket. I'll show you where that's at when we take the tour. I would recommend using that, not when you're taking a weld test, but any other time. It'll help cool down your material. You won't have to wait as long in between welds. So that's it. That was the chapter. Hopefully we survived it together. A lot of information, a lot of material. Like I said, I've also loaded the official 74 slides onto D2L content chapter 8. You can go through all those other slides that we didn't go over on this video. A lot of that material, again, we're going to go over in the shop anyways. I would rather do it, three-dimensionally than just trying to do it off these slides. I hope this information helped you, and I hope that it made the chapter a little bit easier. If you have any questions, you can always email me at dekurtz@hack.edu, and we'll see you in the shop.